Welcome to today's lecture. So we are in our lecture notes, and today we go to section 2.4. We will speak about the Newton Polytope, and this is a, let's say, technical but very nice tool that may help to decide whether a polynomial is a sum of squares of polynomials. And as another technical tool, we will introduce convex sets. So you might probably have heard about convex sets in some context. Probably you have heard about it in the context of R to the n, where R are the real numbers. Or maybe even in real vector spaces. Here we do it more generally, so we don't just take real numbers, we take an arbitrary ordered field, so k together with less than or equal is an ordered field, and we look at a vector space over k. And for those of you who know already much about convex sets, the basic message will be that you can do it in very much the same way, at least the basic things, over an ordered field. And for those of you who have not heard about convex sets, it's just an introduction to convex sets, to the very basics of it. And for those of you who know about convex sets but forgot about it, it's a reminder. Okay, so let k together with less than or equal be an ordered field, V a k vector space, and A a subset of V, when A is called convex, if for all x and y in A, and for all lambda in this interval between 0 and 1, of course this is an interval in this ordered field, so this is with respect to this order. So that means for all lambda that satisfies 0 is less than or equal lambda, and lambda is less than or equal 1 with respect to this less than or equal. Lambda x plus 1 minus lambda y lies in A, right? So of course we have a good intuition, I guess, in R to the n, if k is R and V is R to the n, or maybe let's say R to the 2 even, when we can draw it easily, when we have a very good intuition what that means, right? So that means, okay, you have, whenever you have 2 points in the set, the line segment joining them, right, is also in this set, right? So for example, a set cannot be of this shape here, because here I could choose 2 points such that the line segment between the 2 points is not entirely in the set, right? So how do convex sets look like? Well, you know, a good intuition is that they look a bit like potatoes, right? Not all potatoes are convex, but very often they are approximately convex. Or an egg usually is really convex, right? Up to some fine things that happen on the surface, of course, right? Okay. Yes, so that's the intuition about convex sets. A must can, of course, be open, or it can be open or neither open, neither closed. Everything is possible, right? So they could also be low dimensional, like line segment in R to the 2. This line segment here would also be convex, right? The empty set is convex, the whole space is convex, right? Okay, so convexity, I think, is very well known. Here we do it, of course, in order to believe with intuition, you should of course think about why the points on this line segment joining the 2 points x and y are exactly those which can be written as lambda x plus 1 minus lambda y with lambda in 0, 1, right? But I think, you know, either you see it immediately or maybe some people would prefer a little calculation in order to see it better, because you can write this as x plus, and now let's see, from going from x, we take the vector y minus x, right? This would be the vector y minus x with green vector here. Y minus x, right? So it should be the case that you have here x plus lambda y minus x. Is that right? Oh, maybe 1 minus lambda, that's as good. 1 minus lambda times y minus x, right? Because when you have here x minus, yeah, that's exactly the same thing, right? So if lambda varies between 0 and 1, then 1 minus lambda also varies between 0 and 1, and then, you know, you shorten this vector y minus x, right? You multiply it with a scalar between 0 and 1, so you get all these vectors whose base you can put at x, so that they point to something here in between. Okay, so but that's very basic. Yeah, I think you would all have been able to think about this without my explanations. So the smallest convex superset of A. So why is there a smallest convex superset of A? A smallest convex subset containing A. If A is an arbitrary subset of V. Well, that's, you know, because the intersection of convex sets, an arbitrary intersection of convex sets, and let's say the empty intersection is V, right, is always convex, right? That's clear, right? Easy to see. Okay, and so this intersection over all convex supersets is obviously the smallest convex superset. There can be only one, right? Because there cannot be two smallest. Smallest means it's a convex superset, and whenever you have another convex superset, of course inside V, when it is contained in there, right? And I claim that this smallest convex superset of A consists exactly of these so-called convex combinations of points in A. So I take here finitely many points, so M is the number of points, and maybe I should write here, so this was a bit the sloppy writing. What I meant here is that lambda 1 up to lambda m are non-negative elements from K, and the xi's, x1 up to xm, are in A, and the sum of these coefficients lambda I is 1, right? So such a weighted sum with non-negative weights that sum up to 1, that's called a convex combination, right? That's analogous to a linear combination, right? But we have these two constraints, that the weights are non-negative and they sum up to 1. And the set of all such convex combinations of elements from A, that's called that turns out to be equal to this smallest convex superset, right? That's the convex hull denoted by this. Okay, so why is this the case? Well, I actually wouldn't need even that I wouldn't need to know that the smallest convex superset exists. I mean, I gave a reason for that, but I could see this also just by proving that this is the smallest convex superset, right? So let's see why it is a convex set. Well, you know, I will not do it in detail, but why is it convex? So if you have two such convex combinations, let me just write it very shortly, right? So I have, this is the first convex combination, so I will not write that the lambda i's are in K are non-negative, etc., etc., that the xi's are in A. I will not write this now. So let's say I have this convex combination, and then I have another, right, where the y, j are in A and so on. And then I have a lambda here, and then here 1 minus lambda. And the lambda, of course, should be an element from K between 0 and 1. You know, when this is, of course, it's the sum of lambda, lambda I. And the lambda, lambda I are again non-negative, right? Plus j 1 minus lambda, lambda j, yj, right? And so these are again non-negative, right? And they sum up to 1, right? So the sum overall I, lambda, lambda I, plus the sum overall j, 1 minus lambda, lambda j, is, is lambda times 1 plus 1 minus lambda. Oh, sorry, that was, I did something wrong here. I meant here, of course, mu j's. I wanted to write mu j here also. I'm really sorry. Mu j. Mu j. I shouldn't take the same letter. Okay, and then here I have here times 1 equals 1. Right? And so this is convex, and it of course contains A, because, you know, every element from A, if x is in A, then I could write x as a sum of just one term as 1 minus x, right? And so here I take m equal 1, right? And I take just one lambda. And also so it's a convex superset of A, and why is every other convex superset of A contained in it? Why is it contained in every other convex superset of A? Well, if I have a convex superset of A, I can easily prove that each convex combination, so of elements of a convex set, is actually in the convex set, right? This is trivial for convex combinations of just one element. So if m is here 1, then it's trivial. For m equals 2, that's basically just exactly the definition of convexity, right? Because this is an arbitrary and convex combination of two elements, looks exactly like this. And then for more than 2, now let's do an induction, of course, right? So if I assume I have already shown it for convex combinations of n elements, I can now show it let's say of m elements. Now I can show it for m plus 1 elements in the following way. So I have here lambda. So if lambda m plus 1 is 1 when all the other lambda i's are 0 and when there's nothing to do, right? So without loss of generality, lambda m plus 1 is not 1. When I can here write lambda m plus 1, when I can here write 1 minus lambda m plus 1 times the sum, that was an equal. So that was an equal one. So 1 minus lambda m plus 1 times the lambda I divided by 1 minus lambda m plus 1 from I equal 1 to m, right? And then plus lambda m plus 1 xm plus 1, right? And I see here that, there is missing the xi here, of course. So these things are non-negative, right? This, of course, was also non-negative. And this here is actually a convex combination of m elements, because the sum is convex combination of x1 up to xm, since the sum from I equal 1 to m, lambda I divided by 1 minus lambda m plus 1 is the sum from I equal 1 up to m plus 1 of lambda I. And when I subtract lambda m plus 1 again, and in the denominator I just take what is there. And so this is, since this sum here is 1, I have here 1 minus lambda m plus 1 divided by 1 minus lambda m plus 1, which is 1, right? So this is a convex combination of m elements, and therefore by induction hypothesis it's already in the convex superset we are looking at. And this, of course, is also there, and this is a convex combination, right? Of two elements. So I see here that m plus such a convex combination of m plus 1 elements is also in this superset, right? Okay, so what geometrically, how is the geometric intuition for convex, for this convex hull? So that's actually called the convex hull. Maybe I should mention this. So what is the geometric intuition for the convex hull? It's called the convex set generated by A, or also the convex hull of A. So what's the geometric intuition? Well, okay, you have your set A, right? Let's say A is such a set, has this is part of A, and this is part of A, and then there is this point is part of A, right? So okay, so now the smallest convex superset. Okay, so certainly, I mean, since this point is in there and this point is in there, the whole line segment between them is in there, right? And also like here, this line segment is in there. And also, so I'm wisely choosing already the lines I draw here, right? This is also certainly in there, right? And, now you see that, now you can join this point with every other of these green points or blue points, right? And so on. Yeah, and you see what you get. You get actually, this area here, right? So that's of course an intuition in the real vector space R to the 2, right? But you can easily, I think, imagine R to the 3, and then by analogy you might have an intuition for R to the n, and then a real vector space when you have good intuition for finite dimensional real vector spaces because they are isomorphic to R to the n, and then this is just a little bit more abstract. I have here an ordered field, right? Okay, so and I have a vector space, of course, need not be finite dimensional, and in infinite dimensions it's already very hard to have a good intuition for convex sets. Okay. Since convexity will accompany us also in later chapters, I'm talking really a lot about convexity now, right? And yes, so that's this. That's the convex hull. And we call finitely generated convex sets, that means convex hull of finite sets, we call them polytopes, right? So geometrically, if you start with just, instead of this set here, you start just with a set, you start just with finitely many points. Right, when the corresponding picture is, of course, so a convex hull is, is this, right? So that would be in R2, right? But in R2 or 3, it could be a cube, or it could be a simplex, or more complicated objects, right? So it could be I don't know, it could be you could have a pentagon as a base, and then you could have a pyramid over this, right? It's probably not drawn very well. Something like this. Okay. And so on, right? And so that are polytopes. And of course, polytope could also be low dimensional, like this one. I did not define a notion of dimension, but intuitively you might say that's of dimension 1 in the plane. Or it could be empty. A polytope is thus of a form, well, it's of this form, right? So you have finitely many points. And here I took always in each convex combination arose from finitely many points from A. But if I have a finite set that generates this convex set, I can just involve always every of these generators, right? Because I could take the corresponding lambda, I can be 0 also, right? Here I could also choose twice the same xi, but that's okay. I can just have it once here, because if I have if it appears twice in the sum, then I could the corresponding coefficients, I could just add the corresponding coefficients and could make one term out of it by distributivity, right, of a scalar multiplication. Okay, so if A is a convex set, then a point x in A is called an extreme point of A. And now if it is if x is not the midpoint of a proper of a proper line segment, of a line segment whose endpoints are not the same, right? So let's see, what would be the extreme points in this example here. So first of all, the extreme point has to be an element of a set, right? That's written here. So this red point here is no extreme point because it's not in the set. Okay, is this an extreme point? Well, that's not an extreme point, right? Because it's exactly the midpoint of the following line segment, right? Or of that one. I mean, there are many possibilities, right? Okay, and so it's certainly not. So next question is if this is an extreme point here, this red point here. And again, it is not, because here I have already less choice maybe for a line segment, because it's the midpoint of this little line segment here, right? Well, is this yellow point an extreme point? Well, it looks like, right? Because how would you find a line segment if this is really the corner, so to say? Then yeah, I don't think you find such a line segment here, right? So the extreme points here in this example will be these, yeah, how would you call this? I mean, some people would perhaps call it the corners, but yeah, I think the usual way of saying it is these are the vertices of a polytope, right? Okay, good. So let's define this. Extreme points of polytopes are also called vertices of a polytope. Okay, but let's make more examples concerning extreme points. So what happens if I have just the open unit disk in R2/2, right? So let me draw it. It's something like this, right? So the dashed thing means that boundary should not be included, right? Okay. So what are the extreme points? Well, so this is certainly no extreme point. This is no extreme point, right? Now here, well, actually no point is an extreme point, right? Because these boundary points are not included in the set. You have to be included in the set to be an extreme point. Okay, so here you have no extreme points. What happens if we add the boundary? So now let's add some part of a boundary at least. Let's say this part, right? Looks like a headset. Okay, so I mean that, you know, I take this part of a boundary and these 2 points also should be included, but these points should not be included. So now what are now the extreme points? Well, I think, you know, I guess all this part which I have added on a boundary will now be part of the extreme points, right? So there are many extreme points. A whole segment on this circle consists of extreme points. Okay. And maybe another example. Yes, so let's look at the following example. So I have here, it's like this. I have here a line segment, and then and when I have here a quarter of a this should be 1/4 of a unit disk, of a disk, and when I go on here, and let's say this goes to infinity here. So the picture is as follows. That I have here. Picture is as follows. So what are here the extreme points? Well, these points here, these yellow points are certainly extreme points. Guess this point also looks like being still an extreme point, right? But when there is nothing else, right? So I think you got a good feeling about extreme points. Also, you could have a strip here, right? You could have a strip in R2 two parallel lines, and the things that are in between, right? This is also a convex set, such a strip, and yeah, I actually wanted to delete these things here. Right. Okay, so what are the extreme points here? Well, there are no extreme points, right? There are no extreme points for this strip here. So now you might ask, why did I actually say here x is the midpoint of a line segment between y and z? And remember, y should be different from z. That's of course important. Well, that's actually not important. That's just because that was the easiest thing to say it, right? I could also have looked at other line segments. So, if I have a point in my convex set, which in that case now is with strip, that lies properly on some line segment, but it's not the midpoint of this line segment, but it's not one of the endpoints, right? When that's also a reason why it is not an extreme point, right? Because you could just shorten the longer part of this. I mean, the red point divides the line segment into two parts, and you could just shorten the longer part, right? So I could just take a new line segment where one endpoint is still the same and the other one is closer to the red point, right? And such that the red point is now the midpoint, right? And that's the next exercise. So suppose k less than or equal is an ordered field. V is a k vector space. A is a subset of V. X is in A. And lambda is now not 1/2, but it's any number strictly between 0 and 1 in this ordered field. Then again the following are equivalent. X is an extreme point of A, and there are no y and z in A, such that y is not different from z, such that y is different from z, and x is lambda y plus 1 minus lambda z. Okay, so as I have said, if a negation of what I have just argued geometrically is that if a negation of B is true, so if there are such a Y and Z, if there is such a line segment where X is properly on, when A is not an extreme point. So what I have argued just by shortening this line segment is what I have proven by this. I mean, you should write it up formally, it's very easy, is that A implies B, right? A implies B. And but it's also true that B implies A. For B implies A, you can start with you can assume that so you can, instead of B implies A, you can prove that not A implies not B. That's the same thing, right? What says that? Now if you have not A, so when X is the midpoint of such a line segment, right? And when you find another line segment such that the given point X divides this in a certain ratio, right? Which is pre-specified here by this lambda, right? So that means you have, this is also by shortening, right? That's also shortening the thing so that you get the right ratio, right? So I don't do this now, but it's you should just do it formally. I mean, the picture is anyway clear, but you have to do it formally, of course. Prove it algebraically, let's say, right? And this is very easy. I don't do it, it's a nice exercise. Okay, so, and you know, how you often see it in the textbooks is like they would here not fix the lambda in advance, and they would say here there are no lambda between 0 and 1, and y and z and such things, right? That's formally a little bit weaker, right? Because but that's what we really need, I think. That's what we really need. That A implies B. For the direction A implies B, that amounts to the same thing, right? But B implies A here would be completely trivial if I put the lambda here, if I quantify the lambda here inside B, when B implies A would be trivial, right? But since I fixed the lambda in advance, now B implies A is not completely trivial, is almost the same argument as A implies B. That's a little bit stronger formally. It's always nice to formulate things stronger if I hold a little bit stronger, but that's not very important here. So now our next lemma, let k less than or equal be an ordered field via k vector space. M in n0, x1 up to xm vectors in V, and P be the convex hull, right? P the convex hull of these points, of these finitely many points. And I suppose that none of the given points xi could be dropped. So whenever I take just one point out of my generating set, right, that generates a convex set which is strictly smaller, right? I could also write here strictly smaller, right? Because it's clear that, I didn't prove it now, but if A is a subset of B, both are contained, of course, in my k-vector space, then, of course, the convex hull of A is contained in the convex hull of B, right? Because that's the smallest convex superset of B, but that's also a convex superset of A, and that's the smallest convex superset of A, right? So I think these trivial things I just will use without mentioning it, right? So this actually means that P is not equal, means actually that this convex hull of all but one of these points is properly contained in P, right? And then if you take out even more than one point, it would, of course, still, it would be still be strictly contained, even more strictly usually, right? Okay. So the statement here is that when P is a polytope, well, that's completely trivial because it's a convex hull of finitely many points. But what is really the statement here is that x1 up to xm are its vertices, right? You know, the vertices are the extreme points of a polytope. And so the statement here is really that the xi's are extreme points, right? Yeah, so, you know, I think the intuition is clear, right? So, you have these finitely many points. And they are in such a way that if I take out, so the convex hull would be now, of course, this, right? Now if I take out one of these points, the convex hull gets immediately smaller. So let's just keep the red points and take out one. Now the convex hull gets immediately smaller, and that is true whatever point I take out, right? And then the intuition, I think it's easy to believe that these points are then vertices, are extreme points. And I call them vertices because I have actually a polytope, which is trivial. Okay, so we should prove this formally. So we have to show that every vertex of P equals one of the xi's, right? And second, that every xi is a vertex of P. Clear. So for A, let x be a vertex of P. And now we show it's one of the xi's. So how can we do this? So first of all, since x is an element of P, it is a convex combination of the xi's, right? And I mean, at least one of the lambda i's is not zero, right? So let's say without loss of generality, lambda 1 is not zero, right? You know, because I could interchange the role of the xi's, so that's okay. I could rename the xi's. So without loss of generality, lambda 1 is not zero when lambda 1 is 1, actually. For otherwise, I could define mu as the sum of remaining lambda I, and that's 1 minus lambda 1, and that would be bigger than 0, right? If lambda 1 is not 1, then it's strictly smaller than 1, and when 1 minus lambda 1 is strictly bigger than 0. And then I could write x as a proper linear combination of x1 and this element. So, which contradicts 4.2b, right? Because well, first of all, yeah, so because, you know, I could take for y x1 here, and for z here, I could take this. And I have just to verify that they are not equal. And then the lambda 1 plus mu obviously is 1, right? So that would contradict the given hypothesis that X is a vertex of P. And why is this? So this is in the set P. That's even, so x1 certainly is in P, but right, so, but this is also in P. Why is this in P? Because it's even in the convex hull of x2 up to xm, and therefore in the convex hull of x1 up to xm. And why is this? Well, that's just because the lambda I divided by mu are non-negative, of course, and they sum up. Well, what do they sum up to? They sum up to 1 minus lambda 1 over mu, but mu is 1 minus lambda 1, so they sum up to 1, these coefficients here, and therefore this is a convex combination. So on the other hand, to prove B, we let y and z be in P, and we assume that, or we suppose that x1 is the midpoint of a line segment between y and z. And now we have to show that when y equals z, right? So this line segment is actually trivial. We have to show this. So y and z are themselves linear combinations of the xi's, because they are in P. And so I write them accordingly with coefficients lambda I and mu I. I take such convex combinations. And when we show that lambda 1 is 1 and mu 1 is 1, because when we are done, right, when the other lambda I are 0 and the other mu I are 0, and when y equals x1 and z equals x1, right? And that's what we want to show, right? If we can show it y equals z, then of course y must be x1, and also geometrically that was clear that this was to show. So we have to show that lambda 1 equals 1 and mu 1 equals 1, and it's enough to show that where average is 1, because because we are, you know, lambda 1 plus lambda 1 is less than or equal 1, and mu 1 is less than or equal 1. So if one of them would be strictly smaller than 1, right, then here the numerator would be strictly smaller than 2, and then this cannot be 1. So we have to show just this, that where average is 1, and if it was smaller than 1, then I would have it 1 minus lambda 1 plus mu 1 half, 1 minus this times x1 is the sum from I equal 2 to m of lambda I plus mu I half xi. Well, that I have anyway, right? Because this is just if you put this to the other side of the equation, when, you know, that's just this equation here where I have plugged in my representations of y and z as convex combinations of the xi's, right? So this I have anyway. But now if lambda 1 plus mu 1 half is less than 1, then I could divide by this, right? And it would follow that, and I would get a convex combination on the right-hand side, right? Because, you know, everything would be, all these coefficients are non-negative, because I divided here just by a positive number, and a positive element from my ordered field K. and the sum of the coefficients is 1, right? The sum of these things divided by this is 1, because the sum of these things is exactly this, right? Yeah, which follows from this. So, but when it would follow that x1 is no convex hull of x2 to xm, which by hypothesis was not the case, since that would imply that, of course, that these two convex hulls are the same, right? If x1 were, this equality, I mean, one inclusion is clear that this would always contain in this, but the other inclusion would now also follow, because that's the smallest convex superset of x1, smallest convex set containing every xi. But that's already a convex set. That would be already a convex set containing every xi, because it also contains the x1. So the inclusion from this, so this would be also contained in this. And I would have equality here, but this was P. So P would be the convex hull of x2 to xm contradiction. Okay. Okay, so we have this lemma. And we can actually use this. So to draw the following important corollary, namely that every polytope is the convex hull of its finitely many vertices. Okay, so namely, polytope by definition is the convex hull of finitely many points, right? Right, and now it might be, of course, true that this condition does not apply, so that it might be true that P equals the convex hull of a proper subset of this, right? But if this is the case, then we can drop one of these xi's here, right? For example, x1, and P is still the convex hull of the remaining xi's, right? And now we can go on like this, as long as the condition is not fulfilled. I mean, this condition saying that none of the xi's is redundant here in this equation. We can continue and drop as long, and we can drop until we reach a point where this is satisfied, right? And then these remaining xi's are the vertices of a polytope, and P is the convex hull of them, right? So, okay, so this is actually, there is in fact a theorem of Minkowski, which we will treat later, much later in the course, that if you have a compact set C in Rn, compact, which is equivalent to being bounded and closed, when C is the convex hull of a set of its extreme points, right? And this this is of course closely related, right? But here we had a relatively cheap way of proving what we need for polytopes, because this theorem of Minkowski is somehow more complicated. Good. definition and proposition 245. So suppose K with less than or equal is an ordered field. V is a K vector space, and let A and B be subsets of V, arbitrary subsets of this vector space over this ordered field. When I define the sum, or it's better to say the Minkowski sum of A and B, as the sum of all x plus y, where x is in A and y is in B, right? So as an example, if this is my origin, and let's say the set A is like this, okay, and the set B is, I don't know, is maybe this. Right? Then what is A plus B? Maybe let's put the origin closer. Right, so maybe this is the origin. And what is A plus B? So in order to see this, you have to move this around, right? So you can move this around here. And here I have already prepared some copies, right? And so you know, for each, so yeah, take the union over a lot of translated copies of this blue thing, right? And then we will probably see, when we will see roughly how it looks like, right? So this is nice thing to play. Right, so yeah, I don't know, something like this, right? So yeah, I don't know exactly how it will really look like now, but you know, something like this. Okay, so that's a nice exercise in drawing, right? You should fill the white space here, and so on, right? Okay, good. Anyway, now another example, if this is A, and if B is just, say, something consists just of 2 points, namely the origin and another point. So this is B. Then you know it's pretty clear how A plus B looks like. Namely, that looks something like this, right? And now the convex hull of A plus B, right? The convex hull of A plus B, how does that look like? I guess that should look like this. Right? So the convex hull of A plus B is the convex hull of A plus the convex hull of B. So what's the convex hull of B? that would be this, that would be this line segment here. So that's the convex hull of B. And the convex hull of A would be this, right? That's the convex hull of A. And you see that, and it looks quite plausible, right? That if a convex hull of A plus the convex hull of B gives also the convex hull of A plus B, right? Well, it looks plausible, but you can easily prove it because, you know, well, let's prove it. Yes, I guess I prove it in the proof. Okay, so it's okay, so we will prove it. And so this Minkowski sum is particularly interesting for convex sets, actually. So now let A and B convex. When A plus B is also convex, that follows now, if you accept this already here, when that follows, right? Because if A and B are convex, when they equal their convex hull, so you see that A plus B is the convex hull of A plus B, so A plus B is convex, right? When A plus B is also convex. And if now comes an interesting fact, if Z is an extreme point of A plus B, when there are uniquely determined x in A and y in B, such that Z is x plus y, right? Maybe for this it's interesting to look still at another picture. So if here is the origin, and if I have again a set A, let's take a lens-shaped set here. That's a and I take now convex sets, right? I have this convex set A, and I have maybe this convex set B. B, right? When how does A plus B look like? Well, we have already explained this, but maybe again you could also explain it in this way. You take here a point of A and a point of B, right? And you add them. And I can symbolize this by such a parallelogram, right? So this is X here, this is Y, and this is Z, right? And the set of all sets which I get in this way, right? That's the sum of, that's the Minkowski sum of A plus B. So, and how would that look like? Well, I guess it would look like, you know, something like, I hope I draw something reasonably well. No, I think it would look like more or less like this, right? So, and now comes what I claim here. If you take now an extreme point set here, right? So if set is here, so let me take another set now in blue. Maybe this one is extreme, right? When how could that arise? How could that arise? Well, that could arise only by taking here an extreme point from A, let's say here, Bx, and an extreme point from B, Y, right? And so a corresponding parallelogram is this one, right? If you are extreme here, then that comes from an extreme point here plus an extreme point here. And actually these extreme points are uniquely determined by that one. Okay? And well, even they are unique. So yeah, I could also say this in this way. So this set can arise only in one way by adding points from A and B, right? Other points, for example, this set here could probably arise in several ways, right? Because if you, I mean, you could here, instead of this x, you could take another x nearby, and you could compensate this by taking here another y nearby, right? Probably, right? Well, at least in this example, it looks like this. But if you want to get to an extreme point here, when this is only uniquely possible, first of all, and second, it's only possible by taking extreme points here. Okay? So it looks like a reasonable statement. I think it's not completely clear a priori if that is right, but you can prove it. Okay, so let's now first of all in a proof, let's prove that the sum of a convex hulls is contained in the convex hull of a sum for arbitrary subsets A and B. So when I take something in the convex hull of A, so I take finitely many points of A and non-negative coefficients from a field K, and which sum up to 1, and here I do the same thing for B, right? And so I have here I look at the sum of these two linear combinations, and I want to show that it's a linear combination of elements in I look at the sum of these two convex combinations, and I want to show it's a convex combinations of elements of A plus B. So the trick is perhaps to introduce here artificially the sum of the mu i's, because it's 1, and here sum of the lambda i's, which is also 1, right? And in this case, I can write this as a double summation over I and j. And I have here, each time I have lambda I mu j. And here xi plus yj. Okay. And so the only thing I have to, and the mu I times, the lambda I times mu I are non-negative, and they sum up to 1. That's now a crucial observation, because, you see this is just the expansion of this product, and this is 1 times 1 and so on. Okay. So, and the other inclusion that this is contained here is trivial, right? Because, you have like a linear convex combination like this, right? Where the xi's are in A and the yi's are in B. And you write it like, using distributivity, you write it like this. So that's trivial. Okay. So now let A, B and B be convex when A plus B is also convex. I've already talked about that. Now finally, if set is an extreme point of A plus B, and let x let x in A and y in B with z equals x plus y, when x is an extreme point of A, since if you have x is if you had at x equals x1 plus x2 half with different with distinct x1 x2, when it would follow that set could be written as x1 plus y plus x2 plus y half, right? Obviously. But x1 plus y is different from x2 plus y. And you know x1 plus y is in a plus b, and x2 plus y is also in a plus b. So that would mean z wouldn't be an extreme point, but it was one, right? So contradiction. So in the same way, of course, y is an extreme point of B. Suppose now that x prime is in A and y prime are in B such that z equals x prime plus y prime. So we want to show unicity. So we want to show that x prime equals x and y prime equals y. So, but when we have z equals x plus x prime half plus y prime half, and x plus x prime half is also an extreme point of A. Yeah, we have already shown this, right? You know, we have already, so, you know that x plus x prime half is an element of A, right? And y plus y prime half is an element of B. So I can apply what I've already proved, that if I write Z that as a sum of an element of A and an element of B, that when these things are extreme points, right? So I can apply it also to here. So now I know that this is an extreme point of A. But that's possible, of course. So x plus x prime half, an extreme point of A, that would contradict to a very definition of extreme point if x and x prime were in A, right? So, and were different. If x and x prime were distinct. They are in A actually, right? So they cannot be distinct. So x equals x prime, analogously y equals y prime, of course. Okay. Yes, so that's it. Now notation. Now we come. So now what has this to do with polynomials? So it's that was just tools from the theory of convex sets. Now we come. So we want to see what that has to do with sums of squares and with polynomials. Okay, an important notation which we will use almost any time now. So we often work in polynomial rings over a finite number of variables, over a field usually, right? And so the number of variables we will, if nothing else is said, will be n, right? And when we have a tuple of variables x1 up to xn, and we will just denote this by x underscore. And if A is a commutative ring with 0 not equal 1, so we can build a polynomial ring over A, we denote by A adjoint x underscore, that should stand, of course, for A adjoint x1 up to xn. And for all alpha in an n-tuple of non-negative integers, this will often serve as a tuple of exponents for a monomial, right? So we will denote, so the corresponding monomial will be written in shorthand notation like this: x underscore to the alpha is x1 to the alpha 1 times x2 to the alpha 2, etc. And this is in some sense, let's call this the value of alpha. Value of alpha is just the sum of its components. So it would be the degree of this monomial, right? So let k be a field and take a polynomial in n variables over k, and we can write that then as a sum over all tuples of non-negative integers alpha, n tuples, a alpha x to the alpha, right? With a alpha in k. And okay, this looks like an infinite sum, but it makes sense because it's actually a finite sum, of course, right? So I mean that almost all, or all but finitely many a alpha are 0. And yes, and then this is of course unique. These are just the coefficients of f, they are uniquely determined by f, of course. And the set of all exponents here that actually appear, so set of all exponent tuples alpha such that a alpha such that the corresponding coefficient a alpha is non-zero, that's called the support of f. That's called the support of f. And it's convex, that's a finite subset. I can consider this as a finite subset of R to the n, right? And so that's so if n equals 2, then it's a finite subset of R to the 2. So you know, I have here 1, 2, 3, 4, 5, sorry, 5, and so on. 1, 2, 3, 4. And you know, if I have now a polynomial like 2 times x1 squared x2 minus x1 x2 plus x2 squared minus x plus 1, right? What is then the support? Well, the support is, you know, here I have 2, 1 in the support. When I have 1, 1 in the support. When I have 0, 2 in the support. When I have 1, 0 in the support. And finally, I have the origin in the support. Right, so that's the support. And it's convex hull. So this is f, and this is the support of f. And its convex hull, n of f, is called the Newton Polytope. So our convex hull right? So that's n of f. That's the Newton polytope. It's of course a polytope because it's a convex hull of finitely many points. And that's very useful to consider, right? That contains, you know, in one variable, the Newton polytope is just an interval, of course, and its largest element is the degree, and its lowest is the, you know, is the degree of a monomial of lowest degree, right? So and in the multivariable case, looking at the degree is a very rough thing, right? So so if you know that the degree of a polynomial is at most 3, right? If you know that a polynomial is of degree at most 3, when you just know that its Newton polytope is contained, let me draw it in yellow, is contained here, right? Is contained here. And you see, by speaking about Newton polytopes, I have much finer information, right? I have much finer information. And of course, the support gives even more information. But for some reason, we will see it's for some aims, it's exactly the right thing to look at with Newton Polytope, right? Like for other things, it's important what is the degree of your polynomial. So it depends what you want to look at. The support usually has too much information for many things, and the Newton Polytope for some things is exactly the right thing to look at. So let K be a field and F a polynomial, and in K we say that A is a vertex coefficient of F if there is a vertex alpha of a Newton polytope such that alpha to the x alpha, such that A to the x alpha is a term of F, right? Okay, so let's see, what are the vertex coefficients of our polynomial F here, right? So we have to look at the vertices of a Newton polytope. Let me draw them in yellow. Here is one, here is one, here is one, here is one. That point was also in the support of F, but that's not a vertex of a Newton polytope, right? So what are now our vertex coefficients? Okay, so 2, 1, let me write it here, 1, minus 1, and 1, right? So 2, 1, minus 1, and 1. Sorry if it's not very readable, right? Okay, so what are our vertex coefficients? And since every vertex of a Newton polytope of a polynomial lies in the support of a polynomial, you know, by 2, 4, 3, right? So, you know, because, you know, Newton polytope, we are in this situation here. The Newton polytope is the convex hull of the elements in the support, right? And now I could erase here some of these elements in the support so that it's still the convex hull, right? So I just keep deleting some of these until there is no redundancy anymore. And then I know that the remaining ones are exactly the vertices of a Newton polytope. And so from this I get then that the vertices of a Newton polytope are actually elements in the support, right? Okay, that's not very surprising, but you really have to prove a little thing, but it follows off by this lemma 2, 4, 3. Okay. So since every vertex of a Newton polytope of a polynomial lies in the support of a polynomial, vertex coefficients are always non-zero, right? Because, yeah. Okay. Because of course, by the very definition of a support. Okay. Let K be a field and Fg be polynomials. Now comes first interesting fact. You know that the degree, so if you are working over a field, when the degree of a product of polynomials is actually the sum of the degrees, right? So that's easy to see. And here we have a similar thing, like a Newton polytope of F times G is the Newton polytope of F plus the Newton polytope of G. So we use here this Minkowski addition of convex sets. And moreover, every vertex coefficient of Fg is the product of a vertex coefficient of F with a vertex coefficient of G, right? In the univariate case, you know that the leading coefficient of a product of two polynomials over a field is the leading coefficient of such a product is the product of leading coefficients, right? And here this is a bit similar, right? Every vertex coefficient of fg is a product of a vertex coefficient of f with a vertex coefficient of g. Okay, so let's prove first the thing about Newton polytopes. So first the direction from, okay, so yes, first let's prove that the Newton polytope of fg is contained in the sum of the Newton polytopes, right? So for this, you know, the Newton polytope is the convex hull of a support, right? So the Minkowski sum of two convex sets, we have seen it is convex, right? So this is a convex set. And I want to show that the convex hull of a support of fg is contained in it. And then it's, of course, enough to show that the support of fg is contained in it. So the support of fg, you know, if you know how you multiply, how you multiply two polynomials, you see immediately it is very clear that the support of fg is contained in the support of f plus the support of g. Because how can you produce a monomial in f times g, which is actually appearing? Well, you must arise from multiplying a monomial of f with a monomial of g, right? And no, I mean, it can be that it's a sum of such products, but that doesn't matter. In any way, there must be at least one term in one such product you need to have, otherwise you don't get a coefficient. Okay, so a non-zero coefficient. Okay, so that's clear. And that's, of course, contained in Newton polytope of f plus Newton polytope of g. And therefore, the convex hull here is also because this sum is convex. Okay, good. And the other direction, so nf plus n of g is a polytope by 7, 4, 19. Why is this? Well, that's, you know, the n of f is the convex hull of a finite set, right? A finite, right? And n of g is the convex hull of another finite set, B, right? And when we have learned that that convex hull of A plus convex hull of B equals the convex hull of A plus B. So it's and that's A plus B is obviously again a finite set, right? If A has at most m elements and B has at most n elements, when A plus B has at most m times n elements. Okay. So I quoted here 7, 4, 19, but that was exactly for what I have just told. 7, 4, 19, no, that doesn't make too much sense. Okay, no, 7, 4, 19 we didn't yet have, right? So what we certainly meant is here, this fact here. So it must be 2, 4, 5. I'm sorry for that. By 2, 4, 5. 2, 4, 5. Okay, I have to correct this. So this is a polytope by virtue of 2, 4, 4. It suffices to show that its vertices lie in n of fg. Okay, so yes, because a polytope is a convex hull of its vertices and n of fg is convex, so it's enough to show that the vertices lie in n of fg because they generate a polytope, right? it's enough to show for the generators that they are contained here in the left-hand side. I want to show that this is contained here. Okay, it suffices to show that the vertices are in there. Consider therefore a vertex gamma in n of f plus n of g. Okay, so we even show that gamma lies in the support of f times g. Okay. So we even show that gamma lies in the support of f times g. We would have to show only that it lies in n of fg, but we even show it lies in the support of fg. By 7,4,19, there are uniquely determined alpha in the Newton polytope of f and beta in the Newton polytope of g, such that gamma is a alpha plus beta. And alpha is a vertex of n of f, yeah, because it's an extreme point. And beta is a vertex of n of g. By 2,4,9, we have that alpha is in the support. So vertex coefficients are always non-zero, right? So alpha lies in the support and beta in the support of f respectively g. Right? Because of unicity of alpha and beta, the coefficient of x to the gamma in fg equals the product of respective coefficients of x to the alpha and x to the beta in f and g. Right? I have just one way of producing such a, if such an extreme point of a Newton polytope. So if I multiply two polynomials, if I take an extreme point of a Newton polytope of fg, the corresponding monomial arises just in one way by multiplying a monomial of f and a monomial of g. Right? And therefore, since it's just a product of, so a corresponding coefficient is a product of non-zero elements of a field K. And there is no sum involved, so there cannot be any cancellation. And so it is non-zero. Okay, and so alpha plus beta, which is gamma, is in n of f plus n of g, because it's in support of f plus support of g. So we are done with that. Also, the extra claim follows from the above, right? Yeah. So the extra claim is that every vertex coefficient of f times g, so product of a vertex coefficient of f with a vertex coefficient of g. Right? So I think it became clear during that proof, right? So if I take this f and I take here another polynomial g, whose maybe I won't take a concrete example, but let's say the support of g consists of this point, and this point, right? And so the Newton polytope of g is this. When you see that, how do I get now? You see now that a Newton Polytope of, how do you get coefficients, how do you multiply f and g actually, that's the thing, right? So you have to take each coefficient from f and multiply it, or each monomial from f, which is symbolized by these points here, right? In these points, don't contain the information about the corresponding coefficient. And you have to multiply it with monomials of g, right? And so when you do this, you add the corresponding exponent tuples, right? So and you multiply the coefficients, which you don't see in this picture, right? That's how you multiply. And you do all possible combinations, right? Now you see that that the Newton polytope of f times g is the sum of these Newton polytopes, and yes, so so I don't want to draw it now, but it's easy to visualize everything with Newton polytopes, right? It's not completely trivial, but if you think about it, it's quite easy to believe these things here. But maybe it would be good to draw one more picture illustrating this theorem, right? So let's have a picture that illustrates once more this theorem. Okay, so we have here, let's say we have two variables, and let's say the support of f. Let's say the support of f is, I don't know. These points should lie on a grid, right? But okay. So then let me draw a convex hull, which is the Newton polytope, and that's the convex hull, right? And then I have another polynomial. So this is now the Newton polytope of f. Sorry, that's the Newton polytope of f. So it's, sorry. So that's the Newton polytope of f. When I have a Newton polytope of g, and say this has some points in common, right? So say this and say this. Say this. This is a different one, and this, and maybe this one, right? And okay, so this is the Newton polytope of g, and our Newton polytope of f times g. You know how do you actually compute f times g? Well, you have to take each. So if you expand the product of two polynomials, this polynomial has 4 terms, right? And this one has 1, 2, 3, 4, 5 terms, 5 monomials. So you have each time when you expand it, you get 20 terms. You get the sum of 20 terms, 4 times 5. and you have to multiply each with each. And information that you don't see here is what our coefficients use. So, but you have to multiply each with each, and you have to multiply the corresponding coefficients, and when you get this sum, right? So, yeah, the Newton polytope of f plus g, well, let me see. So here I copied a few times Newton polytope of f, and in this way it will be more easy to see how okay. Okay. So let's see. I think that this will look roughly like. So I hope I do it right. Let me do it. Which color do we take? Orange. So guess it could be something like this. Sorry, I need some. Okay. Could be something like this. Talk. Like this. I hope it's more or less right what I'm doing here. Here is now so that's now sum of the two Newton polytopes, right? And you know and what's the support of a product, right? If you multiply f with g, right, then you get of course what can you get? I mean, you can multiply this monomial with this monomial, right? And this will give you this monomial, right? Or you can multiply this monomial with this monomial, yeah? And this probably gives you this one, right? And so on. So this with this gives you this, I guess, right? And this multiplied with this gives you this, and so on. This multiplied with this gives you probably this. And this multiplied with this gives you this. Right? And now we have here also this one. Okay, so I don't draw everything, right? But there are other, I don't know exactly, but there are other things, maybe here and here and here. I mean, I have 4 terms times 5 terms, can be 20 terms actually, right? Could be, but could also be less, right? Because it could be that there are several ways of getting this one, right? For example, right? There are several that you know, several products of two monomials of one of g and one of f contribute to the same here, and that it cancels out, right? That the sum is 0. But in the end, you don't actually get a coefficient here. So that could perhaps happen, right? But the thing is that so the support of f times g, you cannot say that the support of you couldn't say that the support of f times g, of f times g, you cannot say that this is the support of f plus the support of g, right? You could only say so that will in general not hold, right? So that will in general not hold. But what will always hold is the inclusion, of course, right? But the really nice thing is that that for the Newton polytopes you have equality, right? For the Newton and why is this? Because, you know, for example, because this coefficient must actually be there. There cannot be any cancellation so that there is a coefficient of 0 corresponding to this monomial. And that's because this one arises only by multiplying this one with this one, right? And there is no other possibility, right? And so on, right? And every vertex coefficient of fg is a product of a vertex coefficient of f with a vertex coefficient of g. Right? The coefficient of this monomial is just a product of the coefficient of this monomial in g times the coefficient of this monomial in f, and so on. And this one, the coefficient belonging to this monomial in f times g is just the coefficient of this monomial times the coefficient of this monomial, right? And so on. Yeah, that's the really nice thing about Newton polytopes. Okay. So the next thing is comparatively very easy. Let K be a field and Fg be polynomials when Newton polytope of f plus g is contained in the convex hull of a Newton polytope of f union n of g. Right, that's, I mean, in the univariate case, if you have univariate polynomials, when you know, for example, that the degree of f plus g is less than or equal to the maximum of the degree of f and the degree of g. So this is a bit an analog of this. But this is quite easy, that's quite trivial, right? Because the support of f plus g is clearly contained in the support of f union support of g, right? Must not be equal, right? Because again, it could happen that you add two monomials that the coefficients of the same monomial in f and g neutralize each other when one is minus the other. So that in f and g there could appear monomials that don't appear in the sum anymore. So, but you have this inclusion at least. So, and this is of course contained in the Newton polytope of f union the Newton polytope of g. Now I have here, you know, I have here an inclusion of sets, and of course, if I apply on both sides of this inclusion, the convex hull, the inclusion is still holds, and therefore I have this. Okay. So next thing. So yeah, in general, you know, I have only inclusion here, and you know, it's clear that I mean, for example, if g is minus f, then f plus g is the zero polynomial, and the Newton polytope of a zero polynomial is empty, right? So in general, you certainly don't have here equality. But now let's think, when do we have equality here? Like for univariate polynomials, you know also a case, right? If you have two univariate polynomials of a different degree, and if you add them, then you know that the degree of a sum is the maximum of the degrees, right? So here we have equality. And here there is also a case where you have equality, right? Another case, by the way, in the univariate case, another case where you have equality would be that if the polynomials have the same degree and their leading coefficients have the same sign, right? And here we have a condition which resembles a bit that thing, right? So let K be an ordered field and Fg be polynomials in several variables, such that all vertex coefficients of F and G have the same sign, right? I mean, really the same sign for everyone, right? For the vertex coefficients of F and G. Okay. When we have here equality, the Newton polytope of F plus G equals the convex hull of a Newton polytope of a union of the Newton polytopes, right? And so we will see this in a minute. And all vertex coefficients of F plus G also have this sign. So why is this? So let's look at the proof. So one, the inclusion from here to here always holds, right? That was 2, 4, 11. The other inclusion now, the one that does not always hold. So we have that the convex hull of the union of Newton polytopes is, of course, the convex hull of the supports, right? Well, this is easy, you know, because, I mean, the union of the supports is contained in the union of the Newton polytopes, so the inclusion from right to left is clear, right? The inclusion in the other direction is also easy because, you know, the Newton polytope of F is contained in the right-hand side, right? Because it's a convex hull of a support of F, and it's contained in the convex hull of a bigger set. And in the same way, the Newton polytope of G is contained in the right-hand side, and therefore the union, since the right-hand side is convex, also convex hull is contained in the right-hand side. So that was easy. And so since it's a convex hull of a finite set, right, support of F is finite, support of G is finite, so the union is also finite. So it's a polytope. Let alpha be one of its vertices, right? You know, a polytope is the convex hull of its vertices. So if you want to show that this polytope is contained in the Newton polytope of F plus G, it's enough to show that its vertices are contained in the Newton polytope of F plus G. So we fix one of these vertices, alpha. And then we even show that alpha is actually in the support of F plus G, even that. By 2, 4, 3, alpha lies in at least one of the sets support of F and support of G, right? So, you know, that might be a bit subtle again, but it's easy. You know, we started with a convex hull of union of a support of F and the support of G. And now I can, you know, what I claim is that each vertex of this convex hull of a union is in support of F or in support of G. And that's just because, you know, I can delete redundant things here until there is nothing redundant anymore, and then I know that I have exactly the vertices of this polytope, right? Okay, so alpha lies in at least one of the sets support F and support G. So if alpha lies only in one of these two, then the claim is clear, right? Because when I add, there cannot be any cancellation of coefficients. If on the other hand alpha lies in both, then I have to be careful, because if I add the two polynomials, the same monomial appears twice. If I have bad luck, one coefficient could be minus the other. So if on the other hand alpha lies in both, then alpha is a vertex of both. it's a vertex of Newton Polytope of F and Newton Polytope of G, right? Because alpha was a vertex of a Newton Polytope of F plus G, right? And it's contained in so it's it's an extreme point of n of F plus G, and it's contained in a convex subset, right? And therefore it's also an extreme point of this convex subset. Yeah, I think that's perhaps the easiest argument. So what happens is that you have a polytope. It could be an arbitrary convex set, but let's take a polytope. And you have an extreme point of it, like this one, and now you have a convex subset of a blue set that contains this point, right? So let's draw this in orange. In orange I said. Okay. So let's draw it in orange. Right. And now this is of course also an extreme point of this smaller convex set, right? Because it's not the midpoint of a small line segment in the smaller set, because it's not the midpoint of a small line segment that lies in the bigger set, right? Okay, so it's a vertex of both a Newton Polytope of F and Newton Polytope of G. Okay, so and the coefficients of x to the alpha in F and in G, and hence also in F plus G, have the same sign, right? Because that's now my what I have here, but that's the hypothesis of theorem, because these are vertex coefficients, right? And from which it follows again that alpha is in the support of F plus G, right? Because if you add two positive coefficients, they cannot neutralize each other. When the Newton polytope of when this is proven now, because I wanted to prove that alpha is a Newton polytope of F plus G, I've even proven it's in the support of F plus G. And the extra claim follows from what was shown. So the extra claim was that all vertex coefficients of F plus G also have this sign. I looked actually at an vertex of a Newton polytope of F plus G, right? In hindsight, because I looked at the vertex of this, but it turned out that this is the Newton polytope of F plus G, right? And I had shown that the corresponding coefficient in F plus G has the same sign. Good. Okay. So now another easy thing, let K, very easy lemma, let K be an ordered field via K vector space and A convex subset of V. When A plus A is the same as 2A, now this looks trivial, but it is not completely, because 2A should be defined as the set of all 2x with x in A, right? So this a priori is a different thing, right? So the idea is as follows. So A plus A So you have here your set A. It's a convex set, right? It was a convex set. And when I build A plus A, so how do I get all elements of A plus A? Well, I take here an element, maybe here, and so this point, and then I take another one, so this point, and then let me do this parallelogram again, a parallelogram, and then I get here a point in A plus A. Right, and if I do this with all these, if I choose any two of here, then I don't know, I get something like, yeah, I guess perhaps something like this, right? So that's A, and that's A plus A. And the thing is that I can get each point here also just by taking 2 times a vector from here. And the idea is very easy because you can just take here, you know, the midpoint between these two, and is that right? Yeah, and I think that will do the job. My drawing is not very good then. So, so let's see the proof. So one thing is trivial, and the other inclusion, let xy be in A when x plus y is 2 times x plus y half, and that's in 2A. And with x plus y half, of course, is a convex combination of x and y, and therefore lies in A. And now we come finally to this, after all these preparations, we see what this has to do with squares of polynomials and with sums of squares. First was squares, right? So let K be an ordered field and F a polynomial over K, when the Newton polytope of F squared, of F times F, is 2 times the Newton polytope of F. And all vertex coefficients of F squared are squares of vertex coefficients of F, and therefore positive, right? Vertex coefficients are always non-zero. Okay, now n of F squared is 2 times n of F, follows from, well, you know, normally it would be the Newton polytope of F plus the Newton polytope of F, but that's 2 times the Newton polytope of F. So I use the lemma we have just seen, and 2 for 10, right? With G equals F. Okay. Now, suppose gamma is a vertex of a Newton polytope of F squared, which is also a Newton polytope of F plus the Newton polytope of F. When by 7, 4, 19 there are unically determined alpha and beta in the Newton polytope of F with gamma equals alpha plus beta, right? But then alpha must be equal to beta because, you know, they are unically determined even as a pair, right? So this uniqueness even says that you cannot interchange now. If alpha and beta are not the same, then, you know, beta alpha would be another such pair, but there is only one such pair, right? So actually this pair alpha beta is even unique, right? And if beta alpha is another such pair, then they have to be equal, and then alpha has to be beta. So, you know, because gamma is also beta plus alpha, it follows that alpha is equals beta. But when the coefficient of x to the gamma in F squared is just the coefficient belonging to x to the alpha in F squared, right? Because, coefficient of x to the gamma in f squared. So if you expand the product f times f, there is only one term in this expansion that contributes to the x to the gamma. And this is actually the square of this x to the alpha, of a coefficient belonging to x to the alpha. Okay, so these vertex coefficients are squares and therefore positive. Okay, and now we come finally to the sums of squares, right? So let K be an ordered field, and suppose I have finitely many PIs, polynomials over K in finitely many variables, and I take the sum of squares of these polynomials PI. We call that F. When the Newton Polytope of F is 2 times the convex hull of a Newton Polytopes of a union of a Newton Polytopes of the PIs. You know, if you have a univariate polynomial, for example, over an ordered field, then the degree of this polynomial is 2 times the maximum of degrees, and if you write it as a sum of squares, right, of PIs, then the degree of a polynomial is 2 times the maximum of degree of the PIs. Easy to show, and actually we have shown it. Even more general things we have shown. And here this is an analog which is a bit finer and gives more information even in a multivariate case. And all vertex coefficients of f are positive. Okay. Good. So, and I guess you could even say they are sums of squares, right? Okay, so let's prove this. So that's the thing we will actually need for our sums of squares business. Okay. So this is now easy because we have already done so much. Okay, so for each I, we have that Newton Polytope of pi squared is 2 times the Newton Polytope of pi, we have seen that. And that all vertex coefficients of pi squared are positive. And now if we add polynomials with just positive vertex coefficients, we get again a polynomial with, when we know the Newton Polytope of a sum, right, is equals the convex hull of a union of the Newton polytopes, right? That was because we had this positive vertex coefficients. But now here we know that, this is 2 times n, right? And it's easy to see, very easy to see. I don't do it. It's a little exercise that you can pull out to 2 here. Okay. And that's it. And all vertex coefficients of f are positive. Because those of pi squares were positive. Okay, good. So now finally our famous example, I mean not our example, but the famous or most famous example probably of a polynomial which is non-negative, but not the sum of squares. So in one variable, we know already that each non-negative polynomial over a real closed field is sum of squares. In two variables, that's not true. Even though over reals, it's not true. So take this famous Motzkin polynomial. So in 1967, Motzkin found this example. Yeah, it's got somehow famous, and many people say that it would have been the first example to be the first explicit example to be found that is non-negative but not the sum of squares of polynomials. But I don't think that's true. But anyway, it's not important because it's very well known that Hilbert already in the 19th century could easily have constructed such examples. He had all the knowledge for it, and he just was too lazy to give an explicit one, probably, or he was not interested. Okay, at first, so we show that so this is an example in two variables. I write now x and y instead of x1, x2. It's x to the 4 y squared plus x to the 2 y 4 squared minus 3x squared y squared plus 1. And we have f is non-negative on r squared, but f is not the sum of squares of polynomials. So there is no, polynomial sums of squares certificate for being non-negative. At first, we show that f is non-negative on R2 in three different ways. So first is using the inequality between arithmetic and geometric mean. So in general, this inequality says that for all n in n, and for all a1 up to an in R, the arithmetic mean between VAIs, that is the average, right? The sum divided by n, is greater than or equal the geometric mean. The geometric mean is the nth root of a product of VAIs, right? So it's not so hard to prove using analysis. There are many different proofs for it. So I don't prove it here. I assume that you know it, or otherwise just accept it. Or you don't even have to accept it, because I will show anyway in three different ways that f is non-negative on R2, and I won't use this anywhere else. Okay, so but from this, you have for all ABC non-negative, you have that the arithmetic mean is greater than or equal to the geometric mean. And I can apply this if I take here an x and y in R. I can apply this with a equals x to the 4 y squared, b equals x squared to the x squared y to the 4, and c equal 1, right? And then I deduce, I deduce x squared y squared, right, is less than or equal 1/3 x to the 4 y squared plus x squared y to the 4 plus 1. And then I multiply by 3, and then, So you see, it's just somehow a special case of inequality of arithmetic and geometric means. Okay, so the second proof is, by giving an algebraic certificate for non-negativity. Well, what would be such an algebraic certificate? Well, that would be a sums of squares representation of f, writing f as a sum of squares of polynomials. But that's exactly what we will show, from which we will show that it is impossible, right? So what I do instead is I give a sum of squares representation of this polynomial, where I substitute each variable with its third power. If I can give a sums of squares representation for this polynomial, I know that this polynomial is non-negative, right? You know, but since each real number has a third root, even negative numbers, I mean, each real number is each real number is some other real number cubed, right? Even the negative numbers, of course, right? That's why I take x cubed and y cubed and not x squared and y squared. Oh, that's one of the reasons. Yes, so then this is also a certificate for f being non-negative, right? Okay. And you know, another way of doing this, so that was the third way, but the second way is also another certificate. It's a certificate for 1 plus x squared times f being non-negative. I write that as a sum of squares of polynomials. And that's also enough, right? Because, you know, when you know that if I evaluate f somewhere, then I know that this will be then evaluated to something positive, and I know something positive times the value of f is non-negative, right? So when I know that f is non-negative everywhere also. So let's first do this, 1 plus x squared. So multiply f with 1 plus x squared, and I hope it's the sum of squares of polynomials. Okay, let's maybe again look what was f. How does the Motzkin polynomial look like? So that was f. So I multiply it with 1 plus x squared. So I take first all these terms here, right? And I copy them. And then I multiply each of these terms with x squared, right? And so I get exactly these terms here. And now let me see. So I have here this minus 3 times this, right? That gives that should give minus 2 times this here, right? And then I have here x squared, that gives here the x squared, and then I have here x squared y to the 4, that gives here the x squared y to the 4, and then I have here minus 3x squared y squared, that's strange a bit. Okay. So artificially I write this as this, and this, right? And then I have what is still missing here, the x4 y square of y to the 4. It's just here. And then the x6y squared, x to the 6y squared, that's here. And then the 1 here, right? 1 here is this. Okay. And you know this thing, oh sorry, you know this thing gives this, right? And yeah, exactly, this here gives this, and right, and this gives this, right? But that's the sum of squares. That's a square, that's a square, and that's a square. So it's a sum of 3 squares. Okay, and here is our proof. So let's again look at the definition of f. So I plug in x to the 3 for x and y to the 3 for y. So this becomes this, this becomes this, this becomes this, and this becomes this, right? So now, now this is quite tricky. So let's see, x6 to the so x to the 12, y to the 6. Where do I find this? So this here I have 1/4 of it. Here I have 3/4 of it. So that's okay. So when I have x to the 6, y to the 12. So here I have 1/4 of it. And here I have 3/4 of it. Okay. So when minus 3 x to the 6, x to the 6, y to the 6. So I have here minus 1 times this. And then here again minus 1. And here again, and here actually plus 1/2. And here minus 3/2. Right? And now I have many terms that I have artificially somehow introduced here. So I have here x to the 4y squared. So I should correct this at some point. And that's actually happening here. When I have x to the 8, y to the 4. So here I have minus this actually, and here I have plus 1/4 this. And here I have plus 3/4. So that's also okay. When I have here 1/2 x to the 10, y to the 8. And here 1/4 of it. And then x, and then here minus so when here minus 3/2 plus 3/4. Yes, and that's okay. And then I have here 1/4 x to the 8, y to the 10. Here I have 1/2. And that gives 3/4. X to the 8, y to the 10. X to the 8, y to the okay. Oh, okay. So I did actually something wrong, I guess. You know, there was something wrong. This this is relevant for now, and this was before. Okay, but when it's okay, so so sorry for that, but now it's okay, I guess. When we have this 1/4 plus 1/2 plus 3/4, so that's 6/4, that's 3/2. So I should subtract this at some point, yeah, and that's actually the case because it's subtracted here, right? And now we, okay, need more colors. So x to the 2, y to the 4, that's subtracted here again, right? And then maybe instead of continuing with colors, I just make here a circle. So minus x to the 4, y to the 8, and then plus 1/4, and then plus 3/4. So that's okay. And that's yeah, okay, there is still one thing, there is v1 here, which is here, and that's all, I guess. Yeah, okay, now okay, now let's see. So I have here five lines, 1 2 3 4 5 6. No, it's 6, and here I have 6 squares, and each line gives now a square, namely this line here, right? So this is a square of 3 terms, so if you multiply that out you get 3 squares, right? And you get so that's this one and this one, no, sorry, yeah, and this one and that one, yes. And you get 3 mixed terms, right? And yes, please do it at home, okay, I hope you trust me, and or maybe look at that one, right? And yeah, I think you can do it yourself, right? Now we show so it's non-negative, and we have seen 3 different proofs. So Motzkin polynomial is non-negative, and we have seen 3 different proofs. Now let's see that it is not the sum of squares of polynomials, right? Now let's see that it is not the sum of squares of polynomials. Okay. So what is its that has to do with the Newton polytope. The Newton polytope of f is the convex hull of the support of f. What's the support of f? It's 4 2, 2 4, 2 2, and 0 0. I mean the convex hull of this, right? So, and you see that because the 2 2 here is not necessary, because that's just that's 1/3 times this plus 1/3 times this plus 1/3 times 0 0, right? So that's a convex combination of the 3 hours. So I can forget about this. So it's a convex hull of these 3 points, and here now it's easy to see, that none of these is redundant anymore. So these are the vertices. These are the 3 vertices of a Newton polytope, and And assume that for a contradiction, we assume that f is the sum of squares of polynomials. Is the sum of VPI squared. When the Newton polytopes of VPI are contained in the convex hull of the Newton polytopes of a union of Newton polytopes of VPI, that's trivial. But that's, you know, by what we have learned about the Newton polytopes of sums of squares, that's 1/2 times the Newton polytope of f, which is easily seen to be the convex hull of half of these points, right? And so let's make a picture maybe, right? So okay, so first maybe let's really make a picture from the start. 1, 2, 3, 4, right? So a Newton polytope of so what is the support of f? So of Motzkin polynomial. So this is the support, right? And now this is the Newton polytope of a Motzkin polynomial. And 1/2 of it is now this. And the Newton polytope of VPIs is contained in this. So what points can be points can be in the support of PI? It's only this one. And when it's let me draw it in yellow. It could be this one. It could be this one. It could be this one and this one. There is nothing else, right? And if you want to show this formally, then you easily succeed. Okay, so so there are only these 4 points, which are on this grid and at the same time in the Newton polytope. So only these can be in the support of PI. So the coefficient of x squared y squared in pi squared, you know that's this one, right? So if in pi squared, now the Newton polytope of pi squared is again contained in this one, right? And let's look at the coefficient of x squared y squared in pi squared, right? That must that must be the sum of 2 of these yellow points, of course, right? Or it must be a sum. Yes, yes, of course. And if there is, sorry, not the coefficient, but the coefficient of what can, so if I expand pi times pi, right, then I multiply a monomial of pi with a monomial of pi. That corresponds to adding one of these yellow points to another one of these yellow points, right? And what possibilities are there of adding 2 yellow points so that I get this point 2, 2? Well, if you look what is possible, I mean, adding the 0 actually helps nothing, right? So if I add these 2, then it's already too much, right? It's already too far here outside, right? If I add, so this point has to be involved. And then you see easily that the only possibility is that I have this point plus this point. So, and that means the coefficient of x squared y squared in pi squared is therefore the coefficient of xy in pi squared, right? And therefore non-negative. So the coefficients for each pi, the coefficient corresponding to this monomial is non-negative. The coefficient, this coefficient is non-negative. Yes, sorry, this coefficient is non-negative. And now if I add the pi squares, the coefficients of x squared, y squared, I have to add them. And if I add non-negative numbers, I get a non-negative number. So the coefficient of x squared, y squared in f is also non-negative. But that's not true. It was negative, right? So this shows that f is not the sum of squares. Thus one can neither generalize 2, 1, 1, a to c to polynomials in several variables, right? So that was just a statement that univariate polynomials over real closed fields that are non-negative are sums of squares of polynomials, right? Nor one can generalize 2, 3, 5, a implies b. So that was the thing for quadratic polynomials over Euclidean fields, actually, right? But even for real closed fields or even for the real numbers, you could not generalize it. The statement was that if it's non-negative, if such a quadratic polynomial is non-negative, and it's a sum of n plus 1 squares of linear polynomials, where n is the number of variables. And also, so this for quadratic polynomials are non-negative quadratic polynomials are sums of squares of polynomials, but for higher degree in general not, as we have just seen. Note that the proof shows even more. The proof shows even that even if you add a constant to f, right, if you add a big constant, right, like plus 1000, when f is not just non-negative, it's actually very, very positive somehow, right? Maybe you could think that could help, so that it might make it more probable that it will be a sum of squares after adding such a number. But that's not the case. No matter what constant you add here, it will never be a sum of squares. With exactly the same proof, right? Because we did not even use what is the constant here, right? And by 2.2.6, the Motzkin form, so-called Motzkin form, so that's probably the way Motzkin initially presented his example. That's just a homogenized, that's f homogenized, right? So that's just you take a new variable. Usually we call that x0, but now I call it z, to homogenize with polynomial, right? So I add here a z squared and here a z to the 6, z squared and z to the 6, right? So, and when I get this thing here, and this is positive semi-definite, you know, because its dehomogenization was positive semi-definite, that was 2, 3, 1. But it's likewise no sum of squares of polynomials. You know, because if it were, then, you know, its dehomogenization would also be a sum of squares of polynomials. For being non-negative or for being a sum of squares of polynomials, we saw it didn't matter if you take the homogeneous or the non-homogeneous version. So again, by 2.2.6 for dehomogenizations, now I can dehomogenize with respect to another variable, right? So yes, so now I dehomogenize that thing here, right? So I substitute x by 1. So when I get y squared plus y to the 4th minus 3x squared z squared plus z to the 6th. Or I dehomogenize with respect to the second variable. When I get this thing here, And you know, because this homogeneous thing was not the sum of squares, also these dehomogenizations are not sums of squares. So we get still other examples. And they are non-negative on R2. Okay, so next time we will see that, so don't be depressed, even if you have just seen that non-negativity cannot always be certified by sums of squares of polynomials. We will see next time that it can be certified by sums of squares of rational functions, and that will be very good news. And for this we will use much of the machinery we have developed, right? So now we come back to the things where we really advance the theory now, instead of looking at examples and such things. Okay, thank you. That was it. I hope you will be here next time. And many thanks for listening. Goodbye.